How's everyone doing today?
Great.
Any questions before we get started? It is working. The siphon is going, thankfully. I don't think anyone's moving now. Fish tank is like 8 million pounds later, though. All right. So, plan for this week. We have normal lab this week, so I want to make that clear. Do report to lab as normal. And the plan for this week is to talk about buoyant force. We've been talking the past couple days about matter, types of matter like solids versus fluids, talking about fluid pressure. So now we're going to talk about how fluid pressure causes buoyant force. Any questions or anyone need anything before we get started? All right. In that case, to pick up where we left off, we've been talking about pressure. Pressure, again, is the idea that you exert force over a surface area, you get pressure. And as it affects our daily lives, fluid pressure is caused by being submerged at some depth within a fluid. That includes the air that you are currently surrounded by. And that air exerts a fluid pressure upon your body based on the density of the fluid, the strength of the gravity on this planet, and the depth of fluid above the point you are measuring. If there's 2 miles of atmosphere above you, that depth for the air pressure would be 2 miles. If you are 10 feet deep within a pool, that would be 10 feet of water. This is true of all fluids. So right now, the air pressure is caused by your depth within the air. Water pressure would be caused by your depth within water, so on and so forth. Sound familiar? Questions before continuing on? All right. Now, we are going to take this concept and talk about why it causes the phenomenon of floating. Within physics, we have a specific word for that, and that is buoyancy. So, our discussion for today is, we've been talking about this fluid pressure, where it comes from, and the formula that describes how it increases with depth. And now we're going to take that information and start talking about how it causes floating. We call this phenomenon, the technical term for it is buoyant force. There's a force responsible for the floating phenomenon. We call that force the buoyant force. So when I say buoyant force, I am talking about the force that causes floating. And in order for something to float, it does have to be submerged within a fluid. So I'm going to take this box and I'm going to put it underwater. Because if it wasn't underwater, or not in the water, it couldn't float in the water, correct? You have to be in the fluid you're trying to float in. Now, when we put this cube into this water, that means the siphon worked. That's now too heavy for me to lift. So, we've placed the cube into the water, and now that the cube is in the water is going to exert water pressure upon the cube. As per this formula for pressure, just the definition of pressure, that water pressure is now going to be exerting a force on all of the surface areas of this cube. Now, I'm using a cube because they have flat sides, so it should be pretty easy to see where all the forces are going to point on each of this cube's faces, because the way that pressure works is it always pushes inward or sometimes outward on the surface that it's acting on. And since this cube has a bunch of flat sides, all of those force arrows on all of these surface areas of the cube should point flatward into the cube on each of its sides. Does that make sense? So the pressure from the water is going to exert force into the cube on all of its sides. And the thing about water pressure is, does water pressure stay constant if you go deeper into the water? No. It increases the deeper you go because, to reference the formula from the other day, the deeper into the fluid you go, you plug in a larger depth number, you get more fluid pressure. The deeper in water you go, the more the water pressure is. And that means the lower parts of this object are technically at a higher pressure level than the upper parts. The deeper part down here technically is subject to slightly more pressure than the top part because it is deeper down and there's technically more water above the position of the bottom of this box than above the top of this box. So technically there's more pressure down here than up here. Sound right so far? Now what that means is, and it might not even be all that big a difference. Like if it's a small cube, it's not that much deeper, the pressure difference might not matter that much. However, there is still a pressure difference, and that technically means higher pressure on the lower part of the box, more force acting on the surface areas of the lower part of the box. And so I'm going to start drawing force arrows now. First we're going to add force arrows for the two left and right side faces of this box. The deeper parts of the box have a higher pressure acting on them, therefore there will be more force acting inward on that deeper part of the box than on the upper part of the box. So the arrows down here are just physically bigger than the arrows up here. So on that left-facing side of the cube, all of the water pressure is pushing inward on that flat side, so all those arrows point inward, but the arrows are bigger on the underside of the box. Now, that force isn't going to make the box go anywhere because the box has a right side, and on the right side of the box, all the inward pointing force arrows are going to point rightward. So leftward and rightward just kind of cancel out here. The box isn't going to drift to one side or the other because of water pressure. But the arrows do get bigger on the lower parts. They still cancel out left to right. Like if they're 5 in both directions up here, they're going to cancel out. If they're 20 in both directions down here, they're going to cancel out. So left and right still cancels, but do note the lower part is under more force, under more pressure than the upper parts. Now this doesn't explain floating yet, but it's important to get to that explanation. Now, the left and right sides are constantly scaling down depth. The lower parts of the left and right sides are lower than the upper parts of the left and right sides. What's interesting though, is that the top and bottom faces of the cube are all at one depth. The top of this flat cube, this flat surface here, is one constant depth. So the pressure doesn't change across the flat top of the cube, right? Because it's all at one depth. That means that all of the force arrows acting on the upper part of the cube should all be the same size, because the pressure is constant across the top of the cube, because the depth is constant across the top of the cube. So all of these force arrows are going to be the same size. Water pressure acting inward on the flat top of the cube, those are technically going to point down, which kind of makes sense. There's water above the cube physically pushing the cube downwards. It's the weight of the physical water pushing down on the cube, trying to sink it. So all of those arrows are the same size because they're all the same depth. And on the bottom of the cube, since the bottom is all at one constant depth, all of those arrows are going to be the same size. However, there's two things to note about that. One, the bottom is at a deeper point than the top. The water pressure down here is bigger than the water pressure down here because it's physically deeper into the water. And so the arrows down here will be bigger than these arrows up here. Does that make sense? more pressure, more force on the lower part of the cube. And on the lower part of the cube, inward, the pressure is going to point into the surface. What direction does inward point on the lower flat face of this cube? Up. So, on the lower part of the cube, there's more pressure down here, and that means there's more force acting on this lower surface. And because this lower surface is flat and water pressure has to push inward, all these bigger force arrows point up, whereas these smaller force arrows point down. So, overall then, factoring in all of these force arrows and how they would add together, possibly canceling out, what direction is the net force from the water pressure on this cube? Up. On the left and right sides, everything's going to cancel out evenly. Like we got these two tiny arrows canceling out, these two big arrows canceling out. Left and right are just kind of a wash here, because they both increase at the same rate. Top and bottom, though, there's a clear inequality here, because the downward pointing forces on the top are going to be smaller because they're at less of a depth. Whereas down here, more depth, more pressure, more force arrows pointing up than down. So, whenever you are submerged in a fluid, the net force from the water pressure or fluid pressure points up, because the pressure on the lower side of the item is going to be bigger than the upper side of the item. And that net force is the buoyant force. This is the force that causes floating. So that's why being submerged in a fluid can cause things to float. There's literally a force from the fluid pushing net upwards simply because you are submerged in the fluid subject to its fluid pressure. Now, this force might not always be enough to make you actually float. I always had a hard time floating when I am in the pool, and there's plenty of things that when you throw them in the water, they just sink, right? So, buoyant force does not automatically mean something is going to float. Buoyant force is going to be present whenever you're submerged in a fluid. The question is whether or not the buoyant force is great enough to overcome gravity. If this force equals the weight of the item, it'll float, because then you net force up, force down, cancels out, you just stay where you are. If this force is not greater than gravity, or equal to gravity, that's when you sink. So in order to float, the water has to be exerting enough buoyant force from the greater lower pressure on the surface area of the object or your body in order for you to generate enough buoyant force to actually stay on the surface. Again, a force like this is going to be present whether or not you are actually floating, which is why you tend to just feel lighter in the water, right? Even if you don't float very well, being in the water, you do feel lighter most of the time. That's why a lot of astronauts train in Olympic-sized swimming pools. It's as close to 0 G as you can get without actually getting into a plane or a rocket. So, this is where the buoyant force comes from. Does that explanation sound all right? Okay, now, let's put some math to the buoyant force. There's another term for buoyant force, and that is Archimedes' principle. Since my sinking fish tanks are kind of a bust, let's see if I can jerry-rig something with this beaker instead. So I've now filled this beaker with water. And the water level comes up to about this line. Do we agree? All right. Now the reason we call this Archimedes' principle is because of an observation credited to Greek scientist, philosopher Archimedes. Archimedes, at least the story goes, he noticed that when you add something, bless you, to water, when you put an item, submerge it into water, the water level will rise. So to try to replicate that, I'm going to physically place this iron weight into this beaker of water. Note, bless you, what the water level reading is currently coming to before I do that. And now I'm going to add the iron weight. I probably should have used less water. I am just miscalculating so many things today. It is a Monday, is it not? Bless you. All right. Okay, apologies for changing it, but note the new water level before I add the iron weight. All right, that should be about, I think, 500 milliliters. Does everyone see that line? In fact, I'll even try to mark it with red. Please be visible. All right, that's the water line before I add the weight. Everyone can see that? Now I'm going to add this. And Archimedes noticed that when you add something to water, the water level tends to rise. So now it is over the 600 line, noticeably above that red mark that I placed. Everyone can see that? Now, that object is not floating, so I'm going to go ahead and say the buoyant force on that iron weight is not enough to overcome the weight of the item. We'll talk about that in a second. But when we added the iron weight, the water level increased. Now, is there more water in the beaker? No. So the water level increasing is not because more water has come out of nowhere. It's just because I've added more volume in general to the beaker. When I placed that iron weight in there, I added the volume of the iron weight to the beaker. So the water level increased because now the approximately 100 milliliters of iron is taking up space that the water can no longer occupy. It has pushed 100 milliliters of water out of the way, and that's why it now reads about 600 milliliters instead of the previous 500. I have added 100 milliliters of something, just not water. And that's why we were referring to this today as Archimedes' principle, because the legend goes that Archimedes discovered this in the bathtub. He got into the bathtub and noticed that the water level rose despite the fact he didn't add any water, and he famously used it to calculate the volume of a golden crown that isn't a standard geometric shape. So, pro tip, you can use this to figure out this volume of something if there isn't a dedicated formula for that. Like there isn't a formula for volume of crown, or possibly not even a good formula for volume of hexagonal cylinder. But you can use this trick to discover the volume of anything as long as it sinks. And anyway, because of that legend, we call this formula Archimedes' principle because it involves the amount of water that's been pushed out of the way. What this formula says is that when you place an object into a fluid, like in this case, iron weight into water, that water is going to exert a buoyant force on the object. So this part right here, FB, is force buoyant. The subscript B stands for buoyancy. And the value of that buoyant force is going to be equal to, first, the density of the fluid, because the fluid is what is creating the buoyant force. Next is the volume of the submerged object. So in this case, that would be the volume of this piece of metal, which again is about 100 milliliters. And then absolute value of G, once again, for the strength of gravity on this planet. Absolute value because you don't want the negative that's on the 10, you just want the 10. Kind of literally the same as the pressure formula from the other day. And this formula will tell you the buoyant force that will act on something when you submerge it into any given fluid. So if we wanted to calculate the buoyant force on this piece of iron, we would need to know the density of the water that the iron is in, which is typically considered to be 100 kilograms per meter cubed, or alternatively, milliliters, 1 gram per milliliter. So we need the density of water, which we usually consider a constant. I'd make sure you have that number if you ever need it. I'd write it in the question. We need to know the volume of the submerged object. So that is, again, the volume of the piece of iron, which again is about 100 milliliters. So volume iron, 100 milliliters. And G, for the strength of gravity on this planet. We don't care about the negative because of those absolute value brackets. We just want the strength of the gravity. As long as you know those things, you can find the buoyant force on anything. Question so far? All right. So, sample calculation. I'm going to actually find the buoyant force on that piece of iron. Fluid density is 1,000 kilograms per meter cubed. I just have to make sure that all my units match up. I prefer kilograms, so what I'm going to do is for density of water, I'm going to use 0.001 kilograms per milliliter, since I'm going to use milliliters for my volume unit. So for water density, 0.001. For volume of iron, 100. I should just convert that to liters. I don't know. And then times the strength of gravity on this planet, 10. So 0.001 times 100 times 10, I believe that should give us a buoyant force of 1 Newton. And buoyant force always points up. I want to make that clear. It always points up. It has to for you to float and not sink. So, currently, buoyant force on that piece of iron is approximately 1 Newton. Is that all right? Okay. Now, bless you. Do you think that piece of iron weighs 1 Newton? It doesn't. You might not be able to see this. I'm going to pull it back out of the water. This piece of iron is 1 kilogram, and the weight of 1 kilogram should be mass times G, 1 times 10 newtons. So that thing weighs 10 newtons, and the buoyant force acting on it is only 1 newton, and that is why it sinks. Its weight is bigger than the buoyant force. They still have to add together, because to determine net force, you add all the forces together. But, 10 down plus 1 up is a net force of 9 down, therefore it sinks. It doesn't sink as fast as it would fall if the water wasn't there, but it still sinks. And that's one of the rules for whether something floats or not. If the buoyant force is not equal to weight, weight is bigger, net force points down, you sink. Is that all right? All right. That said, I'm going to write the formula up on the board so you have access to it when I switch tabs. FB equals fluid density times submerged object volume I should label these. Fluid times volume, object, submerged, times magnitude of G. So, let's look at a couple more examples. I tried to make them straightforward in terms of the numbers involved. We're going to change our focus away from that piece of iron and instead look at these 3 boxes that have fallen into the ocean. You've got 3 cubes that have fallen off of a cargo ship. One of these cubes is 1 meter by 1 meter by 1 meter. It is in the water, it has sunk. Second one of these cubes is 2 meters by 2 meters by 2 meters. It has also sunk. Third cube is 1 by 1 by 1 again, but it is currently floating. Half of it is sticking out of the water. And we're going to find the buoyant force on all 3 of these things. To do that, we need to know, according to the formula, 1, density of the fluid they're floating in. Since this is the ocean, we're going to treat it as salt water, which is slightly denser than fresh water. Fresh water is 1,000 kilograms per meter cubed. Salt water is 1,025 kilograms per meter cubed. So, density of the fluid. (1,025 kilograms per meter cubed). And we have 3 objects. Volume 1. First is this cube. Its dimensions are 1 meter by 1 meter by 1 meter. What should its volume be? One, correct. Volume of a cube is just length times width times height. 1 times 1 times 1 is 1 meter cubed, which would be this square, but extended 1 meter out from the board, which is a pretty big cube. Now, the second cube is 2 by 2 by 2. So 2 meters by 2 meters by 2 meters is 8 meters cubed. 4 times 2, yes. So twice as big in each axis, but takes up 8 times as much space. That's the volume of cube 2. And cube 3 is 1 by 1 by 1 again. So the cube 3's total volume is also just 1 meter cubed. And strength of G on this planet is 10 meters per second squared. So we've got everything we need to do this formula 3 times and find 3 different buoyant forces. Sound all right? Bless you. Bless you. So, we take these numbers, we throw them into the buoyant force formula 3 different times. First up, buoyant force of the first cube. We want water density times the volume of the item times the strength of gravity. So the fluid density is going to be the same for all 3 of these because all 3 of them are in salt water. So salt water density times the volume of our first cube, which we determined is 1 meter cubed, and then strength of gravity on this planet is 10. The buoyant force on cube number 1 should be 10,250 newtons up, which is a lot. Keep in mind, 1 meter cubed is a lot of volume, which would have a lot of surface area. So there's a lot of flat faces on that particular cube for the water to exert force on. The bigger the item, usually the bigger the buoyant force, because it takes up more space, and that means it pushes more water out of the way. To demonstrate, let's now calculate the buoyant force on object 2. Buoyant force 2. Pretty much everything is the same in this next calculation, except that box 2 is just simply bigger. Still the same fluid density, but the box has a volume of 8 meters cubed, and strength of gravity is unchanged. So, by multiplying the volume by 8 the buoyant force will be 8 times greater. So 80-something thousand at least. 82,000? Thank you. So the same salt water, the same planet, the bigger item generated more buoyant force, and that's because it pushes more water out of the way. The more water something pushes out of the way, the greater the buoyant force on it will be. Have you ever noticed, say when you're at the beach or the pool, or insert your favorite body of water here, beach balls tend to float pretty easily. They'll just kind of hover there on the surface, almost completely exposed. Maybe a tiny bit of them is under the water, just big thing full of air, doesn't really sink. It's not in danger of sinking. You ever notice that when you push the whole thing under the water, it's gonna rocket back up when you let go of it? I'm not the only one that played that game. When you submerge the entire beach ball, you've got a lot of volume under the water's surface, and so it has displaced a lot of water. And when you jam the whole thing under there, you very dramatically increase the buoyant force acting on it if you shove the whole beach ball under the water's surface. And in fact, the increase will be bigger than ×8 because you're going from a very tiny amount of the ball underwater to the whole ball underwater. And so when the buoyant force is really, really big, stronger than the weight of the item, the object rockets back upwards until they equalize. So if buoyant force is bigger than gravity, you actually rise. Questions on the first two? All right. Lastly, let's look at this last object. Now, it has the same total volume as the first cube, but it is currently floating with half of its volume currently sticking out of the water. How is that going to change our math? The rule for the buoyant force formula same water density and same strength of gravity. But the rule for the buoyant force formula is the volume you plug in has to be the volume of the object that is under the water's surface, not necessarily the total volume of the object. And that's because the water only knows about the part of the object that is under it. The ocean is physically unaware of the half of this cube that is above the water's surface. Only the bottom half that is under the water has displaced any water. To try to show what I'm talking about, I'm going to put this thing back into the water, but I'm going to physically hold it here, half exposed. It didn't increase all the way to 600. It's only hovering at about like 550. And that's because if the whole thing's not under the water, if only half of it's under the water, it only displaces half the water, and therefore it only generates half the buoyant force. Because the amount of buoyant force you create is directly tied to the amount of water you displace. So if the box's total volume is 1, and half of it is sticking out of the water, how much volume is under the water? .5. Total volume is 1. Half of that 1 is under the water. Therefore, the amount of cube under the water surface is only half of 1, which is 0.5. So you wouldn't plug in the cube's entire volume, you only plug in the half of it that is under the water, because that is the only part of it that is currently generating any buoyant force. And as a result, that cube should have half the buoyant force acting on it. So 5,125. So, remember, the rules for this formula, you need the density of the fluid, because the fluid is the thing that is creating the buoyant force. If you know the density of the solid object, great, but this is not the formula you use it in. Does that make sense? That's because the solid object is not generating its own buoyant force. The water is generating the buoyant force, so we care about the water's density for this part. Then, you only care about the volume that is under the surface. If the whole thing's underwater, you use the whole thing, but if part of it is sticking out of the surface, you only use the part of it that's under. And then G is again just 10, the absolute value brackets, get rid of the negative sign. How's the formula feel? Any objections or concerns? All right. Make sure you bring any notes for today to lab this week, because lab this week is about buoyancy and therefore this formula. So, we found the buoyant force on all these cubes. I'm going to ask a couple of concept questions about this scenario before we break for the day. First concept question related to this whole situation. I stated a second ago that these cubes have fallen into salt water. They fell off of a cargo ship into the ocean. That is why we used the density of salt water in this formula. First concept question. What would change about this if they instead fell into fresh water, which is ever so slightly less dense? Salt water is more dense because it has more stuff in it. Fresh water is less dense, so how would that change our numbers? They go down. Very good. If you plug in a smaller density of fluid, you're going to get less buoyant force because you're multiplying in a smaller number. That means that denser fluids make more buoyant force than less dense fluids. That means it's actually harder to float in fresh water than it is in salt water. Ignoring, like, when you go to the beach, ignoring the complication of waves, it is easier to float in the ocean than it is in a lake, broadly speaking. That is just because salt water is more dense. If you have ever been to Salt Lake, you might have had a pretty easy time floating because that water is just too dang salty. If you've ever been to the Dead Sea, it's probably been a very weird experience because that water is really salty and really gunky. But that is the easiest body of water for a human to float in because it is the saltiest water on the planet. So it's easy to float in, but it's not pleasant. It's so salty, it's sludgy. So, buyer beware if you go to the Dead Sea. So, thing to note, it's easier to float in a denser fluid. Fresh water is usually considered like the baseline. The denser things get, the easier it is to float in it, but I wouldn't fill the pool with something more dense than ocean water. You could maybe fill it with like syrup, but then you've got other problems for other reasons. All right. Before we break, let's talk about the rules for floating. In order for something to be floating, the current amount of buoyant force upward has to cancel out with the weight of the item. To kind of look back at these three numbers that we calculated, the first two cubes sank because they weigh more than this buoyant force. These are very heavy cubes. Like these cargo containers would probably be all the way filled with solid iron or something like that. So these two weigh more than these two buoyant forces that we calculated. For something to float, the buoyant force up has to add to and cancel out the gravity downwards, very much the same way as if you're sitting on a flat surface, gravity down and normal force up have to cancel out. Literally, it's the same thing. It's just caused by water instead of a solid surface. So to be actively floating, buoyant force and gravity have to cancel out. If gravity is bigger than buoyant force, you sink. If gravity is weaker than buoyant force, you'll actually rise until the two equalize. I mentioned earlier what happens if you shove the whole beach ball underwater. Since in that scenario, buoyant force is bigger than gravity, it rises back until they equalize. And that's why a lot of floating objects are only partially exposed. They keep as much under the water as they need to generate the correct amount of buoyant force. Which, in my experience, is why floating, like people floating, can be pretty tricky, because we're about as dense as water. Oftentimes humans can kind of float. The question is whether or not the buoyant force is enough to push your head out of the water, because that's the part that breathes. So it's a question of, is enough volume under the water to push your head up and allow you to breathe while floating? That's kind of the issue as it relates to humans. But again, the rules for floating: gravity's bigger than buoyant force, it sinks. If gravity's weaker than buoyant force, it rises. If they're equal, you will stay where you are. It's actually possible for some things to just kind of float. Like, they don't quite sink, they go down like 10 meters and they stay there. And that's just the point where the pressure, the buoyant force, and the gravity have equalized, and it just remains there. It'll sink until it equalizes, and for very heavy things, that doesn't happen until they hit bottom. But there's another way to think about it that you've probably heard more commonly, and rather than comparing the strength of buoyant force to gravity, some people just straight up compare the densities of the two materials. You probably heard that rule before. Things float if they are less dense than water, and they sink if they are more dense than water. That is true. That math actually does come from this formula. If you are more dense than water, the weight of the water you displace is less than the weight of the item, therefore the buoyant force is less than the weight of the object and it sinks. If you are less dense than water, the weight of the item is less than the water that it displaced, and it will float. So if you want to float in water, you need to make sure that your density is less than water. And that's why things like wood and styrofoam that are less dense float, and why things that are more dense, like iron, sink. Sound good? All right, so that's why things float. I don't know if you have any questions, and do make sure to bring these notes to lab this week, whenever that is for you. Let me know if you need anything. In case everyone